In this final clip, we'll spend a few moments connecting the technical concepts covered in this module to system-level issues. At the onset, we motivated our study of sensors as a way for us to better understand the environment around us. A developing area that leverages sensors, actuators, embedded computing, and networking is the Internet of Things. In order for us to be able to effectively manage systems such as smart homes and precision agriculture, we need to understand what the state of the environment is around us. We use sensors to accomplish this. In short, while sensors can be very simplistic electrical components, they can play a critical role in systems that serve a wide range of purposes. When designing a system that involves sensing, or any system for that matter, it is first important to clarify what the goal is of the design. For example, the goal of developing a smart home system might be to reduce overall energy use. And thus employing sensors to monitor light, temperature, etc. would be advantageous. We also want to ensure that we employ sustainable practices in our design. This would influence the choice of components. As an example, we noted that some light sensors may require the use of cadmium sulfide. However, it should be noted that this is a Class II carcinogen, which mostly means there are cradle-to-grave issues associated with these type of components. The sensors we considered in this module can be purchased in many cases for pennies. That being said, the conditioning of these devices and the requisite calibrations can be quite costly. The resulting performance, that is the mapping between the parameter of interest and the output voltage, can be characterized in terms of accuracy, precision, noise, drift, etc. The tighter these requirements are, the more costly the system becomes. That is, cost is going to be proportional to the required performance. We discussed the idea of design layers indirectly when we considered strain gauges. While the highest layer objective of the system is to understand the mechanical forces on the structure of interest, this we do not measure directly. Instead, we designed a system that be considered at a much lower layer and that uses a change in voltage resistance in a gauge. That change in resistance is used to determine the strain in the gauge, which we argue is equivalent to the strain in the structure that the gauge is bonded to. It is that strain, accounting for Young's modulus, that gives us the applied force that we're interested in. A strain gauge is just one way to measure these forces. Other approaches, and perhaps less convenient, might include optical methods, but as long as they meet the upper layer objective, the approach is valid. We discussed in our sun tracker example the various subsystems involved in that design. Specifically, we had sensors and the conditioning circuitry that produced a voltage that varied with the phenomena of interest, the microcontroller and its code, and then the linear actuator. So in this application, there's a clear flow of information that is signals between these subsystems. So this voltage output goes to the microcontroller and its code decide what to do with it, and then provide a new voltage to control the linear actuator. There will also be other subsystems needed to complete the design, such as power to the devices and the packaging, and each one of these subsystems needs its own designs, specifications, and testing to ensure the system as a whole will operate properly. The final system-level consideration deals with conflicts resulting in design trade-offs. Cost is often the biggest driver and is influenced by public concerns such as safety, environment, etc. Often we consider component or device costs, but life cycle costs may be more important based on the user's perspective. So let's represent this idea in terms of a graph where we have time on the x-axis and cost on the y-axis. As an example, a temperature control system that implements a simple resistive network to condition the thermistor response may be cheaper to build but may lead to less efficient operation over its lifetime than a system where the nonlinear output of that sensor gets compensated for with a more costly design using a microcontroller. So we could have our resistive design starting off low in cost, but over time having that as system costs, as opposed to something with a microcontroller that maybe starts off a little bit more costly, but over time is less costly to operate. To conclude this clip and the module as a whole, it is worth noting that regardless of the system you are designing as an engineer, considering these 7 tenets will give you perspective on how successful your design may be once it leaves your desk.